Okay, so we're gonna look at some things with trigonometry. Some of this stuff, a lot of it you've seen before in 30-1. We are gonna extend some of the skills that you learned in 30-1 with respect to working with some trig identities. We'll look at a few that are a little more complicated. So we got this chapter. The next chapter is derivatives of trig functions. And then we finish off with antiderivatives, which is the opposite of derivatives. So we'll see what they are used for. But first, trig functions. You saw in 30-1 that angles can be measured in both degrees or radians. The measure of an angle in radians is the ratio of the arc length that subtends the angle at the center of the circle to the radius of that circle. Because arc length and sector angles are proportional, an arc is a portion of the circumference, so the ratio of the arc length over the entire circumference will equal the ratio of the sector angle. So the sector angle is the angle at the center. So you got an angle at the center, and those arms extend, those two radii extend to the circumference, and that portion of the circumference is the arc length. So the ratio of the arc length over the circumference, which is the full distance around the circle, it's an arc length right around 360 degrees. That ratio equals the ratio of the sector angle over a full turn angle, which again is 360 degrees. So we're asked to determine the measure of an angle subtended at the center of a circle with a radius capital R indicated by the arc length. Okay? So we have this relationship up above, that the arc length, which is in this case is 2R, we're going to use that relationship above. The arc length will be 2R divided by the circumference. And you remember the formula for circumference of a circle is 2 pi r. That's the formula for circumference of a circle. And that equals theta, the sector angle, that's what we're trying to find, over a full turn angle, which we will write in terms of radians because on the left-hand side on the bottom, we have that in terms of pi. So we'll write our full turn angle in terms of pi as well. So to solve for theta, you cross multiply. 2 pi r times theta will equal 4 pi r. And then theta can be found by dividing both sides by 2 pi r. And so the r's cancel, the pi's cancel. You're left with 4 divided by 2, which is 2 radians. Because our full turn angle is in terms of radians, our answer will be in terms of radians. So a central angle would be 2 radians, so that the arc length is twice the length of the radius. This next one, what if the arc length is 5 times the radius? So again, if we use that relationship from above, that the arc length, which in this case is 5 times the radius, over the circumference, which again is 2 pi r, that must equal theta over the full turn angle, which again is 2 pi radians. So if we cross multiply, and then divide both sides by 2 pi r to get theta by itself. Once again, on the right side, the pi's and the r's cancel. You're left with 10 divided by 2, which is 5 radians. And it's no coincidence that in both cases, the answer we get is the coefficient of r for the arc length. Okay. But this relationship is something that we never work with in 30-1. We just work with the arc length formula, which was that arc length equals theta over, sorry, just having a drew a blank just now. Arc length equals A equals R theta. Sorry, there we go. A equals R theta, or theta equals A over R, the radius. So that was the formula that we worked with in 30-1. So we've extended a little bit here with this relationship. Okay. You learned that 1 radian is the measure of an angle that subtends an arc length equal in length to the radius. And we know that 2 pi radians is equal to 360 degrees. So therefore, pi radians is equal to 180 degrees. Right? And we use these relationships extensively in 30-1. If you take this statement, pi radians is 180, and you divide both sides by 2, then pi over 2 equaled 90 degrees. If you take that original statement, pi radians is 180 degrees, and you divide them both by 4, so you'll get pi over 4 on the left. On the right, 180 divided by 4 is 45 degrees. Again, if you take this original statement, pi radians is 180 degrees, and now you divide both sides by 3. Pi over 3 would be 60 degrees. And if you take that original statement and divide both sides by 6, 180 divided by 6 is 30 degrees. So those are all the relationships that we worked with in 30-1, and we use them on the unit circle. So we saw that this relationship can be used to convert from radians to degrees and back again. So if we start with that base relationship that pi radians is 180 degrees, if you divide both sides by pi, pi divided by pi is 1, so you'll have 1 radian equals 180 degrees over pi. So if you have 4 radians, like question 1 below is asking us to work with, we want to convert that to degrees. To make this 4 radians, you'd multiply the left side by 4 and the right side by 4. So it'd be 4 times 180 over pi. And so what you have to remember is that the number of radians as a number is always going to be much smaller than the number of degrees. So the number of degrees as a number is much larger than it is in radians. So in this case, our answer has to get larger, and we can get it by taking the 4, multiplying by 180, and dividing by pi. This will give you a bigger number. So 4 times 180 divided by pi is 229 degrees approximately. And we'll have to round that because pi is an irrational number. So we're going to see 2 different types of angles in terms of radians that we're going to convert. These first 3, you just have the number of radians as a rational number. But the ones below are multiples of pi, and we'll handle those a little bit differently. But for the ones above, again, to go from radians to degrees, you multiply by 180 and divide by pi. So 1.5 radians will be 1.5 times 180, which will be 270 divided by pi. .9 or approximately 86 degrees. I don't think it didn't tell us what to round to, so we'll just round to the nearest degree. And 0.6 radians will be 0.6 times 180 over pi. because it's 34 degrees. Okay, so we did some of this in 30-1. Now for these next ones, it's still in radians, but they are multiples of pi. And so for these, we remember that pi radians is 180 degrees. So pi over 3 will be 180 over 3, which is 60 degrees, which, again, we have this one above. That's one of the conversions we did above. Negative 5 pi by 6 radians will be negative 5 times 180 over 6, because, again, pi radians is 180 degrees. So negative 5 times 180 divided by 6 is negative 150 degrees. We also learned that if there is no unit, that means that the angle is in radians. If it's degrees, there'll be a degree symbol. So they can write radians, they can write rad, but you don't even need any unit at all. If you're giving the measure of an angle and no units are given, that means radians. So for number 6, again, we'll let pi equal 180 degrees. So is that 135, I think, or negative 135? Yep. And again, we write it in degrees because that's the unit. Okay? Now, if you want to convert from degrees to radians, again, we know that pi radians is equal to 180 degrees. So in this case, we would divide both sides by 180 degrees. And that'll give us that 1 degree on the right equals pi over 180 radians. Again, when you write your angle as a radian, the number is going to be much smaller than it is as a degree. And so that's why you multiply by pi and then divide by 180. You're multiplying by approximately 3.14, which is going to make your answer bigger, but then when you divide by 180, it's going to get quite a bit smaller than what you started with. So if you have 30 degrees and you want to write that in radians, it'll be taking this expression that we just wrote above, and you're going to multiply both sides by 30. 30 degrees on the right will equal 30 pi over 180 on the left, which again, you can divide top and bottom by 30 to reduce that. You get pi on 6 radians. And again, when no unit is written, it means radians. Negative 135 degrees in radians will be negative 135 pi over 180. These are both divisible by 4, which will give us negative 3, by 45, I meant. Negative 3 pi on 4 radians. For 540 degrees, it'll be 540 pi over 180. These are both divisible by 60 for sure. That'll be 9 pi over 3, which is actually 3 pi. And if you used your calculator and went 540 divided by 180 at the start, you would have got your 3 that way. And negative 38 degrees will be negative 38 pi over 180. And again, if you divide top and bottom by 2, it'll be negative 19 pi over 90. And so there's your answer in radians. Again, no unit written means you're in radians. So there's that arc length formula, A equals R theta, where the sector angle is theta and R is the radius. You have to remember that if you're using this, though, that your angle has to be in radians. And it says that up above there. Theta must be in radians. So for the first one, if we have a radius of 6.5 centimeter and a sector angle of 2.4 radians, we can find the arc length by just subbing those two numbers in. r, the radius, is 6.5 centimeters times theta, which is 2.4 radians. And so the arc will be a distance, the length of that arc will be a distance, and it'll be the same unit as the radius, which in this case is centimeters. So we're going to go 6.5 times 2.4. So 15.6 centimeters. And for question B, we have to first convert the degrees to radians, because when you use the arc length formula, your angle has to be in radians. So if we're going to get a number of radians, our answer must get smaller. And because of that, we have to multiply by pi and then divide by 180. And that'll convert it into radians. So 75 divided by 180 is that decimal. If I write it as a fraction, 5 over 12. So 5 pi over 12 radians, which we could have got by dividing top and bottom by 15, I think. But now we have the angle in radians. Now we can find our arc length by taking r, the radius, and multiplying by 5 pi over 12. So 6.5 times 5 pi divided by 12. So approximately 8.5 centimeters. A circle has a radius of 3 centimeters, angle subtends an arc of 4.4 centimeters. What is the measure of the central angle correct to the nearest tenth of a degree? So if we use our arc length formula, remember this gives us theta in radians. We've got an arc length of 4.4 centimeters. Our radius is 3 centimeters. To solve for theta, we will divide both sides by 3 centimeters, which means that on the left, the centimeters are going to cancel, and you're just left with theta equaling whatever you get when you divide 4.4 by 3. Which is that repeating decimal, 1.46 repeating, but that is in radians. And now we want to write that in degrees. Theta in degrees. And again, when we write an angle in degrees, it's going to be a much larger number than it is in radians, which means you have to multiply by 180. So your answer gets bigger. And then divide by pi. So that decimal we'll keep in our calculator, multiply by 180, divided by pi. So to the nearest tenth, it'll be 84.0 degrees. Okay, so this is nothing new than what we learned about in 30-1. We also talked about rotation angles in 30-1. If a point x, y lies on the terminal arm of an angle in standard position, which remember means that your initial arm is on the positive x-axis, we can sketch the reference triangle and state the 6 trig ratios for the reference angle. So we're not told where our terminal arm lies, so let's draw this one in the first quadrant, and then we'll look at examples where the quadrant changes. But for now, let's use the first quadrant. So P, X, comma, Y lies on that rotation arm, on the terminal arm. Which means to get there, you're going to go X to the right and Y up. And remember that the hypotenuse of this triangle comes from, again, your terminal arm, which is the radius of the circle. Right? In many cases, we used a unit circle where the radius was 1, but it doesn't always have to be 1. But if it's not, you can't use what we learned about the unit circle before. And so we've got our 6 trig ratios, the first 3 being our primary trig ratios. Remember the sine of theta, which is opposite over hypotenuse. And theta, the reference angle, is the angle between the terminal arm and the x-axis. So sine, which is opposite over hypotenuse, will be y over r. Cosine is adjacent over hypotenuse. That'll be x over r. And tangent, opposite over adjacent, will be y over x. So those are our 3 primary ratios. But remember, we also had 3 reciprocal ratios. The reciprocal of sine is the cosecant of theta. It's the reciprocal of sine, so it'll be r over y. The reciprocal of cosine is the secant of theta, which will be r over x. And the reciprocal of tangent will be the cotan of theta, which will be x over y. So there's our ratios. We also looked at trig identities in 30-1. So those are the 8 that we use extensively. We already talked about these first 3. Those are our reciprocal ratios. We also talked about the fact that tan was sine over cos, therefore cotan was cos over sine. We use this Pythagorean identity extensively in 30-1. For all values of theta, sine theta, all squared, which is what sine squared theta means, plus cos theta all squared equals 1. And then we had these other ones that came directly from the Pythagorean identity. Remember, if you took this original Pythagorean identity that I've underlined here, and you divide all 3 terms by sine squared theta, that gives you this one right there. If you divide all 3 terms by sine squared theta. If you take the original Pythagorean identity and divide all 3 terms by cos squared theta, that's where this other one comes from. Okay, so these will be on a formula sheet for you. You don't have to memorize them. You'll be given them, and I'll send out the formula sheet for photocopying so I can give you guys these so you can start using it. It's the same one you'll get for the final exam. So 0.5 negative 4 lies on the terminal arm of a rotation angle in standard position. So this means that you're in the 4th quadrant, because you got to go 5 to the right and 4 down. So maybe something like that. We always draw a line perpendicular to the x-axis from the end of our terminal arm. Theta, the reference angle, is always between the terminal arm and the x-axis. And in this case, we went 5 units to the right and 4 units down. So even though distance can't be negative, we put the negative there so that our cast rule works. Remember, that tells us which ratios are positive in which quadrants. In the 4th quadrant, cosine has to be positive. And then the reciprocal ratio, the secant, will be positive. Everything else will be negative, and we'll see that happen. Before we can do that, we need to find the length of the hypotenuse, which we'll just label it as r. R squared. By Pythagorean theorem, that'll be 5 squared plus negative 4 squared. Right, I'm just using c squared equals a squared plus b squared. So we'll get 25 plus 16, which is 41. So r will equal the root of 41. So that's our hypotenuse. So we've got first our three primary ratios. The sine of theta, which is opposite over hypotenuse, negative 4 over root 41. But remember, you should never leave answers with irrational denominators. We need to rationalize it by multiplying top and bottom by root 41. So there's the answer in simplest form. The cosine of theta is adjacent over hypotenuse. And again, we'll multiply top and bottom by root 41. And then we have our tan of theta, which is opposite over adjacent, negative 4 over 5. So again, if you look at this, the sine and tan are negative, the cosine is positive, and that's what the cast rule tells us. Our three reciprocal ratios then, the cosecant is the reciprocal of sine. It'll be root 41 over negative 4. Our secant, which is the reciprocal of cosine, it'll be root 41 over 5. And our cotan, which is the reciprocal of tan, will be 5 over negative 4. So we saw ones like this in 30-1. We're given the value of the cosine of theta. We're also told that, again, we're in the fourth quadrant because theta is between 3 pi on 2 and 2 pi. Determine the other 5 trig ratios. So if we draw this one, again, because of the domain we're given between 3 pi on 2 and 2 pi, that means that we must be in the fourth quadrant. So there's our terminal arm. We draw a line straight to the x-axis to give us our reference triangle, and theta, the reference angle, is always between the terminal arm and the x-axis. You with us, Brighton? So the cosine, which remember is adjacent over hypotenuse, is 2 over 3. So the adjacent has to be 2, the hypotenuse has to be 3. We can find the length of the third side, again using Pythagorean theorem. A squared plus b squared equals c squared. So in the last one we said r squared. Instead we said x squared plus y squared equals r squared. It doesn't matter. But in this case, you're trying to find one of the legs of the triangle, either A or B. It just depends. If we say that the side that's labeled as 2 is A, then that means B would be the other leg, and that's what we find. So 2 squared plus b squared equals 3 squared. If you subtract the 2 squared from both sides, it'll be 9 take away 4, which is 5. And b will equal the root of 5, which again must be labeled as negative because you're going downwards from the x-axis. So it doesn't mean that the length is negative, it just means you're going that many units downwards. And again, that negative sign needs to be there so that our cast rule is satisfied. So we've got the sine of theta, which again is opposite over hypotenuse. It'll be negative root 5 over 3. We already have our cosine of theta given, so now we need the tan of theta. Opposite over adjacent will be negative root 5 over 2. And now we want our three reciprocal ratios. The reciprocal of sine is the cosecant. That'll be 3 over negative root 5. which we must rationalize. And when a fraction is negative, it doesn't matter whether you rate it as the top negative, bottom negative, or just the fraction as a whole being negative. So there's the cosecant. The secant is the reciprocal of cosine. Cosine is 2/3, so the secant will be 3/2. And the cotan of theta, the reciprocal of tan, which again is negative 2 over root 5, which we rationalize by multiplying top and bottom by root 5. And there is our answer. Okay, so again, we've seen ones like this in 30-1. This next one, the cotan is 3. In this case, we're between pi and 3 pi on 2, which is the third quadrant. We just want to get the value of secant, which is the reciprocal of cosine. But we'll start by setting up our coordinate grid. And we need to draw an angle in the third quadrant because that's between pi and 3 pi on 2. We always draw a line perpendicular to the x-axis. Theta, the reference angle, is always between the terminal arm and the x-axis. And in this case here, we're told the cotan is 3, which means the tan is 1 over 3, the reciprocal. And tan is opposite over adjacent. And in this case, they both must be negative because from the origin you're going left, that makes the 3 negative, and down makes the 1 negative. Again, the length of those sides are not negative, but because you're going left and down, they're both negative, which again will make sure that the cast rule is satisfied. Again, we want the secant, which is a reciprocal of the cosine. To find cosine, we need to know the length of the hypotenuse. So that's where we'll start. So we'll get 1 plus 9, which is 10, and c will equal root 10. And the hypotenuse is always positive because it's always on an angle. Again, this is so that the cast rule works. We want the secant, which is the reciprocal of cosine. So the cosine of theta, which is adjacent over hypotenuse, will be negative 3 over root 10. So the secant will be the reciprocal of that, negative root 10 over 3. No, because we were asked to state the secant. That's what we're looking for. So we just use that to get the secant. Silly Ben. So if cosine of theta is negative 3/5, and in this case we're in the second quadrant, we need to show that that Pythagorean identity that we had previously actually works. Okay. So we start by again setting up our x-y axes. In this case, we're between pi on 2 and pi, so that's in that second quadrant. So we can draw a terminal arm there. And again, we always draw a line from the end of the terminal arm perpendicular to the x-axis. Our reference angle theta is between the terminal arm and the x-axis. And cosine, which is adjacent over hypotenuse, is negative 3/5. So the adjacent side must be the negative one because you're going left from the origin. But again, the hypotenuse is always positive. We're going to need the third side here. So negative 3 squared plus, we'll say that third side, the missing one, we'll just label it as y for now, equals 5 squared. So y squared will be 5 squared, which is 25. Take away negative 3 all squared, which is 9. So So y squared will equal 16, therefore y equals 4. And that's a positive 4 because you're going upwards from the x-axis. So again, we want to show that that identity is true. That 1 plus the cotan squared theta equals the cosecant squared theta. So cotan squared theta means the cotan of theta all squared. The tangent will be 4 over negative 3, opposite over hypotenuse. 4 over negative 3, so the cotan will be the reciprocal, negative 3 over 4. And that should equal the cosecant of theta all squared. Cosecant is the reciprocal of sine. The sine is 4/5, so the cosecant has to be 5/4. And again, that's also squared. So on the right side, when you square the numerator and denominator, you get 25 over 16, and you get the same thing on the left side. So when you square negative 3, you'll get 9 over 4 squared is 16. To add these together, you need a common denominator, so we would write 1 as 16 over 16. And 16 plus 9 does equal 25 over 16. So we've shown that that identity does work. Not only for this specific triangle, but it'll work for all values of theta, except where we have non-permissive values. And remember, cotan is cos over sine. So sine theta cannot equal 0 because you have a denominator of sine. When you write cotan as cos over sine. And that's the same denominator for the right side because cosecant is 1 over sine. Doesn't matter that it's squared, 0 squared is still 0. So we will talk about restrictions on our trig functions. And remember, from the unit circle, we can see where the sine of theta equals 0. Remember, the unit circle is a circle with a radius of 1. So to get to this point, you're going 1 to the right and 0 units up or down. This is 0, 1. This is negative 1, 0, 0, negative 1. And then you have to remember as well that the first number at each point on the unit circle tells you the cosine of that angle. The second number tells you the sine. So the spots where the sine is 0 is there and there. So theta cannot equal every multiple of pi. When n is 0, 0 times pi is 0. That's this point right here. When n is 1, 1 pi takes us right there, where sine is 0. When n is negative 1, again, it goes in a clockwise direction, but you still end up in the same spot. When n is 2, 2 pi takes you all the way around. You end up at the starting point, and so on. So theta cannot equal n pi, where n is an element of integers, are the restrictions on that identity. For practice, on page 252, we can do questions 1 through 4, and then on 253, 1 through 10. I will post these on Google Classroom so you can check the answers. Okay?